Good morning to everyone. I am Dr. Sumi MS. The name of the course is Electromagnetic Fields and today's lecture topic is Normal Incidence onto a Perfect Conductor. On completion, the students will be able to understand the characteristics of a uniform plane wave which is being incident upon a perfect conductor. A uniform plane wave is considered which is x directed electric field and it is normally incident upon a perfect conducting plane with z equal to 0 as in the given diagram. So here the presence of a boundary will give rise to a reflected wave across the negative z direction. So the wave is incident across positive z direction and the wave is being reflected across the negative z direction, and there are no fields within the perfect conductor, hence we consider z as 0. The known incident fields traveling in the positive z direction can be given as ei of z comma t and h I of z comma t, whereas the reflected fields propagating along the negative z direction can be obtained similarly as er of z comma t and hr of z comma t, where eta naught is the intrinsic impedance of free space, which is given as the square root of the ratio of mu naught to epsilon naught, where mu naught and epsilon naught are the permeability and permittivity of free space, and the constant k is written as the product of the angular velocity to the square root of mu naught epsilon naught. Here the negative sign difference in the spatial exponential phase factors represent that the waves are traveling in opposite directions, and the amplitude of this incident as well as reflected magnetic fields can be obtained by the ratio of the electric field amplitude to the wave impedance. The negative sign in front of the reflected magnetic field for the wave arises because the power flow in the reflected wave must also be in the negative z direction. So this diagram represents a uniform plane wave which is incident upon a perfect conductor which is having a zero electric field at the conducting surface, and here the wave is reflected along the negative z direction, and the total electric and magnetic fields are 90° out of phase in time and space. So here the total electric and magnetic fields are just the sum of the reflected and incident fields, and the only unknown parameter Er can be evaluated, that is the reflected electric field can be evaluated from the boundary condition at z equal to 0, where the tangential component of the electric field is observed to be continuous and also 0 along the perfect conductor. So the total fields are obtained as the sum of the incident and the reflected fields in both the electric and magnetic field components. The electric and magnetic fields are 90° out of phase with each other in time and space, and we note that the two oppositely traveling wave solutions are combined, resulting in a standing wave solution. Since this does not propagate, it is resulting in a standing sinusoidal wave solution in space whose amplitude is varying sinusoidally in time, and a surface current flows on the perfect conductor at z equal to 0 due to the discontinuity in the tangential component of the magnetic field. So the force per unit area on the conductor is given as radiation pressure. It is obtained from the given equation, F is equal to half K into mu naught H, and this force on the surface current is observed to be proportional to the average value of the magnetic field on each side of the boundary. Quiz questions on normal incidence onto a perfect conductor. Determine the characteristics of a uniform plane wave incident on a perfect conductor. Thank you.